pulses, didn't we? Fructokinase, right? And so there were multiple elements. I think citrate regulated it, but what's the feature that's kind of astounding about it, and was we went over it a couple of times. What aspect of that regulation is kind of counterintuitive? Well, there's 2,6, yeah. That's just so weird. I just don't even like to. I think we're gonna revisit that with this. There's an integration of metabolism one that I'm gonna kind of build up and hit on that. But what else about phosphofructokinase?
It requires ATP, but ATP inhibits it.
Exactly, right. And so because it,
It requires ATP, but ATP inhibits it.
right, remember that graph where at increasing concentrations, so at low concentrations, it's just a typical logarithmic function, but then you have this negative cooperativity at higher, right? So, yeah, and so if it's doing that, then is that competitive inhibition at the active site?
Allosteric.
It's allosteric at another place, right?
He said that, yes.
So ATP can bind to phosphofructokinase at 2 places, and at higher concentrations it's binding to the allosteric site and shutting it down. Okay? So I think that pretty much covers. Is there any other regulation? I think that's a lot of it. There's needing to understand phosphorylase. Yes?
You said for the phosphorylated regulated that PSK was one of them, but I thought we said in class that it was pyruvate kinase.
Well, no, I didn't say PSK. You said pyruvate kinase, yeah. Okay. All right. Carry on.
Wait, it's not PSK because he did say.
No, he said kinase.
But right now he said PSK.
It's different. He said
She's talking about something
covalent
before?
modification. Yeah.
But it's not covalently. See this, right? Just try to, compare and contrast. Look, right, for all the similarities, and just. Okay. Yeah, right. That's an aspect of the forest, isn't it? Right. So.
What about is there more regulation as we go on?
So I was talking about phosphorylase, right? So then, just get it squared away in your mind. There are all these slides about phosphorylase, right? So there's got to be at least one, if not 2, questions.
When you say phosphorylation,
Glycogen phosphorylase, right? So metabolism, it's the one that binds the inorganic phosphate, right? And it's going to cleave. It's not going to hydrolyze. It's going to cleave the glycogen, right? I guess we did leave out. There's also the kinase that phosphorylates phosphorylase, right? But I looked at that and it falls into the same category also.
the PP1 protein.
Oh, that's the phosphatase. That's the reversal, right? So just anyway. So there's 2 ways to regulate phosphorylase, right? Generally, what's one? Just general modes. Yeah, covalent, right? Phosphorylation, and then the other. No. Well, so what's the effects then of the hormonal regulation, right? It's a cascade, right? And what's it going to culminate in? Phosphorylation, right? Okay. So what's the other mode, though? Allosteric, small molecules, right? So the energy charge or the glucose, depending on whether you're liver or muscle, right? So just kind of know that. everybody squared away with that?
Is it small molecules
Like the AMP, right, or the glucose, right? So the AMP was muscle, wasn't it? Is right in the muscle, and then wasn't it glucose in the liver? Like if the liver is if you have a high concentration of glucose, right, then do you want to be catabolizing your glycogen? No, right? You want to be synthesizing, right? So, seems right to me. All right, what other kind of things? Okay, is Amanda here? Amanda Wynn? Where's Amanda? Hi. Amanda, I'm sorry I didn't write back to you. Amanda sent me an email at 12:34 last night. Normally I'm up that late and I would respond to you, but somehow I had actually gone to sleep. So, okay, so Amanda asked about the names. Amanda, I hope you don't mind. I'm just going to discourage y'all from, please feel free to write and ask about this stuff. So anyway, about the names, knowing the names for the complexes in oxidative phosphorylation, right? So, I've said, no, don't memorize these names. Okay, you need to know the names of the key regulatory enzymes, but say not the names of these complexes. But then I got thinking about it, and that's an excellent example of what I'm trying to get y'all to do, and that is, because your question, Amanda, wasn't it like, so one of them is an oxidoreductase and sometimes called an oxidase, or oxidoreductase sometimes called a reductase, and then the other is oxidase or just cytochrome C, or right? And I didn't know the answer. I would have had to go back to the PowerPoint slides or the textbook because I don't know. And as I famously say, I don't care. Okay, so how many complexes are there? 4. How many of them are pumps?
3.
3. Okay, so how many, then what else is kind of irregular about, there's one out of those 4 that's kind of irregular. It's in the TCA cycle, right? And it's connected through which carrier of electrons? FAD, right? And so because of that, it's below in the potential of electron flow, so we get fewer ATP out of it, right? So there's that aspect. So then above that, we've got the higher potential, the NAD, right? So we have 2 places where we can come in, right? One with the higher potential NAD, one with the lower potential FAD, or NADH, FADH2. So those come in those 2 places, and then in the membrane, we've got 2 kinds of carriers, right? A small molecule and a large molecule? No. There's a slide, and it shows the 2 types of carriers. What are they? Cytochrome C, it's a protein, it's a small protein. Cytochrome C from a bug could probably supplant our cytochrome, highly conserved, right? So we have these 2 carriers, and one of them is Q, is coenzyme Q, and that means it's this ubiquinone, right? Not to be confused with coenzyme A, which is a thioester, right? That has this adenine, this base on it, right? They're 2 the letters look the same, the names look the same, but they're 2 completely different animals. One of them is a carrier of electrons, the other is a thioester to move stuff around, right? So that's what else we know about it. So the NAD is going to pass it then. When it gets the NADH, when it gets oxidized by the first one, it's going to pass it to what? Q, right? To this ubiquinone, right? And it's going to, and through a network of iron sulfur clusters and so on and so forth, and then the Q, and then Q is going to go on to where?
Cytochrome BC.
Exactly. And so it's got electrons, so it's gonna pass them then to what?
Cytochrome C.
Cytochrome C, right? So it's, what's gonna happen to the cytochrome C at that first place there in number 3? Cytochrome C is gonna get
Pump out of the protein.
It's going to get attacked by a big bird. Right? Cytochrome C is waiting there. Is its tank full or empty? It's empty, right? So it's going to get reduced, right? So then that first one, Amanda, she's trying to ignore me. So what's the first one? Is it an oxidase or reductase? Don't think me. We just said we were going to reduce cytochrome C, right? Didn't we? So what's that first one? It's a reductase, right?
And the second one is oxidase. Because it's losing.
Maybe you should write on the board.
I ain't writing anything on it. No writing.
Why?
He's getting flushed.
Yeah. No, really. No, so, I mean, no, so the cytochrome C is getting reduced by that enzyme, right? So it's a reductase, right? Okay, then cytochrome C is now reduced, and it's going to go to number 4. Or I guess I should go this way because it went right. I'm sure. So it's going over here to number 4, right? And now what's going to happen to it?
Oxidase.
It's going to get oxidized. So what is number 4?
Cytochrome oxidase.
Oxidase, right? So you see there, we didn't have to know their names because we know their names. Right?
I feel like that's what you say, like, don't memorize, know it. Like, that's exactly what you said, but that is memorize and understand.
No, it's not. But did we memorize that?
Yeah.
Okay, so here's the deal. So, okay, this is photosynthesis.
What is he doing?
Okay?
Yeah.
So glucose, right? Then I get down here, I'm getting oxidized, right? And now NADH is reduced, right? And then get cut in half and everything, and then maybe I'm down about here, and now I'm acetyl-CoA, right? And then we're passing this to NAD, right? So we got NADH and FADH2. So now say I'm NADH, and down there will be FADH2. And so you're just going to go down, right? So if NADH coming here to 1, right? I'm out of breath, just one second. Sad. So, okay, and then FADH2, right? Coming in here to 2, right? And then it was going to be Q, ubiquinol was going to go on then down here to 3, right? Pass it to 3, that's the... right, it's cytochrome C is going to get reduced by the reductase, and then cytochrome C is going to go on down to 4, right? It's cytochrome C is going to get oxidized, that's the oxidase, and then what happens? Where do those electrons go? Oxygen. To molecular oxygen to make water, right?
Bam.
So that water that from our respiration, those are the electrons from your glucose or your fatty acid. So water is electrons that have reduced molecular oxygen. Or you can say, the other way is that stuff got oxidized. But it's all stepwise, right? So it's better to think of just molecular oxygen getting reduced by the 4th one. Okay, so that's why I just say it all just kind of makes sense, and you don't have to memorize the names of these things. All right? God, I have a heart attack.